Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you understand equipotentials, their relationship to electric fields, and how they fit into Newtonian physics. So what we're looking at here, we have this just region in space here. That's just referring to this. And there's a 2,000 Newton per Coulomb field in the minus I direction. So this is a field strength, what I would call an E sub O here, the magnitude of an electric field, and there's our direction. Let's see, first thing says to draw electric field lines for this field. So little reminder, electric field lines are ways of visualizing the electric fields. They are always tangent to the electric field vectors, and the spacing indicates field strength. So what that means is as the field lines get closer together, the spacing, that means a stronger electric field. And as the field lines get further apart, that means a weaker electric field. Now here we have a uniform electric field. So when we draw the field lines, they should have equal spacing. Now, if I had my, if this was in my other program here, I would use a tool to do this, and I'd get a better situation, but just humor me. So there's a bunch of, oops, that one's probably not good. Let me redraw this. So what I'm trying to do is draw horizontal lines at roughly constant spacing. Not done a good job of that. Try again here. Roughly like this. Good enough. And the electric field directions are this way. Now these lines themselves, these are not vectors, right? These are just lines that represent the electric field. Now they're not perfectly spaced, but humor me and imagine that these distances like here to here, here to here, here to here, here to here were about the same. Right? So the electric field lines might look something like that. I think I'm going to go back and maybe fix this one right here. That's probably a little better. Okay, there we go. So draw electric field lines for this field. Done that. Next, draw equipotentials through the following points. So I'm going to draw the equipotentials. Oh, this is a nice color right here, this magenta or whatever. We'll draw the equipotentials in this color. So let's see, 0, 5. And these distances are in centimeters. And all these are as well. So 0, 5 is here. Now, an important thing to remember about equipotentials, they always make a right angle to the electric field. So the equipotential that goes through that point looks like this. Right, 5, 0. Let's see, so 5, 0 is here. And again, the equipotentials need to make a right angle to the electric field, so they look like this. Let's see, -5, -5 is left 5, down 5, that's about here. Okay. The equipotential through that point. Looks like this. Let's see, and 15, 5. So 15, 5 is basically here. Whoops, no, it's not. 5 is up here. So 15, 5 is about here, give or take. The equipotential looks like this. Again, right angles everywhere. All right, so there I've drawn equipotentials everywhere. Now I've got this kind of big gap. I'm going to go ahead and just draw one more right there, even though it didn't say to. Now, label the potentials and find values, assuming potential at 0 is 0. So basically, this assumption right here is talking about this one right there. Now, potentials, like potential energy, it's an energy concept. You can define the 0 anywhere you want. So let's go ahead and calculate values here. Now, potential differences. The difference in potential between any two locations, we'll say difference in potential is field strength times distance. And right now, let's just talk magnitude here, not worry about plus or minus. And the field strength you use and the distance have to be in the same direction. So for example, if we move from position 1 to position 2, this distance does not matter because we are not changing in potential. You only change in potential when you move into the field or with the field. So our potential difference here between these field lines, our distance is 5 centimeters. 5 centimeters here, here. Again, imagine my diagram's perfect. These distances are all roughly 5 centimeters. So what I'm going to do is calculate the potential difference between any two of these, which would be, I'm going to take my field strength, 2,000 newtons per coulomb, and multiply by the distance between them. Now the distance between them is 5 centimeters, or 0.05 meters. And what we're going to get here, I believe we get 100 volts, or 100 Newton meter per coulomb. When we multiply that all out, I'm pretty sure, right? 2,000 times 0.05. 2 times 5 is 10. 1, 2, 3. 1, 2. Yeah, that looks right. Just double check here. Is yeah, all right, 100 Newton meters per coulomb. Again, brain is not fully functional this morning as I've not had all my coffee. So this 100 Newton meter per coulomb, right, another way to write that would be 100 joules per coulomb. That's what the units of potential are. Or, you know, a joule per coulomb has its own special name. It's 100 volts. So now we can actually calculate values here for all of these different potentials. Now remember, this one, the potential was set to 0. The distance between these two lines, like this distance, is the 5 centimeters. The potential difference is 100 volts. And because we are downstream, if you will, of the 0, the actual value here is 1 minus 100 volts for this potential. Going the other way, right, the difference in potential between these two, here and here, again, is 100 volts. So this one now, the potential is plus 100 volts. This one right here, the potential is now is 200 volts. Let me write this. Right. 200 volts is the potential of that line, and then this one is 300 volts, and so forth. Now, you can put a 0 anywhere you want, right? Had we put the 0 here, right, this one would be 100, this one 200, 300, 400, right? Just a couple more examples. Had we put the 0 here, this one right here would be minus 100, this one minus 200, minus 300, minus 400. Again, you can put a 0 anywhere you want. The only thing that ever matters are differences in potential. And regardless of where you put the 0, if you go from here to say here, you are going to be dropping by 200 volts, regardless of where you put the 0. So there are the potentials, kind of sketched out, labeled. Right now, moving on. How much work is needed to move a proton from 0, 0 to 10, to 10, 5? So now in our picture, we're talking about a proton. I'll go ahead and just use, actually, let me use orange for that. So imagine we got a proton right here. And we want to move it to, let's see, 10, 5. That's about here. Now, if we want to do that, we have to apply a force. How do I want to put this? Let's consider this from an energy standpoint. So let's call this position 1 and this position 2. And now what we're going to do is we're going to write out the work energy theorem for this, just like we always would. So PE1 plus KE1 plus work from 1 to 2 is equal to PE2 plus KE2, right? Good old-fashioned work energy theorem from Physics 1 applies to Physics 2 and everywhere else as well. Now, nobody said anything about moving this proton fast. Nobody said anything about changes in speed or anything like this. So we're going to say, all right, these things are the same. Now, our PE1 term, remember that electric potential, how it's defined. Electric potential is defined as potential energy per unit charge, right? So if you just do a slight rearrangement of this, PE1 can be written charge times potential 1. PE2 can be written charge times potential 2. And again, I'm just setting those kinetic energies to 0. And the value for potential 1 is 0. Right? So remember, we're sitting here, and this was defined to have a potential energy of 0, so this term is gone. Okay? So the work from 1 to 2 is going to equal mathematically here. Let's put in some numbers. The charge of a proton, 1.6 times 10 to the minus 19th coulombs, times the value of potential 2, which was 200 joules per coulomb. Pretty sure I'm going to just lift that picture up to make sure I got that right. Yep. Okay, and when we multiply this out, let's see, I'm going to just do this. This is going to be 320 by the time we take 1.6 times 200, and then times 10 to the minus 19th. And the units, coulombs times joules per coulomb, that gives us joules. Now, I know that this is not proper scientific notation, and to that I'd say, so what? I'm just going to leave it alone. 320 times 10 to the minus 19th joules is perfectly acceptable. Okay, part D. If a proton is released from this position, what will its speed be when it moves through 0, 5? So now we're talking about our proton leaving from here. I'm going to leave that label as position 2. Now remember, the field is to the left. So this proton would accelerate to the left. And let's see, 0, 5. So what I'm going to do is label 0, 5 is here. I'm going to label that as position 3. And we're just going to write a work energy theorem now between positions 2 and 3. So we say potential energy 2 plus kinetic energy 2 plus work from 2 to 3 equals potential energy 3 plus kinetic energy 3. PE2 can be written charge times potential 2, and we have a value for potential 2. KE2 is 0. Work is 0. I'll come back and describe that here, why that is in a minute. PE3 is charge times potential 3, and then KE3 can be written 1/2 m velocity at 3 squared. Now, as I'm imagining here somebody's probably saying, why do we have a work term here and not here? Well, because to move the proton from here to 1015, that would require some sort of external force. Somebody would have to push this way on that proton, and that would be an external force doing work. We don't have that here. The only thing that's doing work on that proton is the electric field. And we are taking it into account by choice using potential energy terms here and here, very much like you would with a gravity problem, you know, a ball drop from a certain height type of thing. Now, the potential at x equals 0, I believe, was 0. I'm going to go back and double check that in the picture. Yep, remember this potential right here was defined to be 0. So in our work energy theorem, that means this is 0, 0, 0. I'm going to just put numbers in here. Charge of a proton is 1.6 times 10 to the minus 19th coulombs. Oh, let's make that so that you can read it or see it. Okay, 1.6 times 10 to the minus 19th coulombs. There is our charge of a proton. Potential 2, if I remember right, was 200 joules per coulomb. Just going to go back to my picture and triple check that. Yep. Okay. Equals, and I'm whoops, got about all my zeros there. Plus 0 equals 0 plus, putting in a numerical value, 1/2 the mass of a proton is, 1.67 times 10 to the minus 27th kilograms times V3 squared. And what I'm going to do, I'm not going to show the algebra here. I'm just going to go ahead and calculate the value. This might take me a moment here. Oh, I got basically 2 times 10 to the 5th. I'll just put approximately 2 times 10 to the 5th meter per second. Just one final comment here, video is getting a little long, but this 10 to the 5th meter per second, that might seem a little fast, but in the atomic world, in the world of electrons and protons and things like that, that's the speed of molasses. Something's not really moving fast in the atomic world until you start approaching like 10 to the 7th meter per second. And when you start approaching 10 to the 8th meter per second, all right, relative standard Newtonian physics starts not working so well, and you have to apply other types of physics called relativistic physics. But again, you don't have to worry about that until you're approaching 10 to the 8th meter per second. So anyway, this video here is just meant to show or help you understand the relationship between electric fields and electric field lines. I'm sorry, electric field lines and equipotentials. Remember that the equipotentials always have to make a right angle to the electric fields and the electric field lines. Another important fact here, you can define a 0 anywhere you want, like we did. Potential increases in this picture going this way, it decreases going this way. You calculate differences in potential by field strength times distance. Now, when the field is constant, that's a nice algebra problem here, basically, just multiplication. When you have variable electric fields, it requires a bit more math. And then, what are these potentials used for? Well, for energy calculations and work calculations, this kind of stuff. So I hope that this video has helped you understand this stuff a little better. Have a great day.